Good? All right. Hey guys, how's everyone doing? Thank you. Um, so I'll apologize in advance on this talk. I think it's mostly developer focused on the data side, but hopefully it's interesting. So the topic of this talk is unifying Bitcoin metaprotocols with GraphQL. So just an overview of what I'll be talking about. First, the general problem we're facing. So I'm the CEO at Rebar Labs. Rebar Labs is primarily on the infrastructure side, building software to connect users with mining pools and help mining pools with block building. But secondary to that, one of our missions is transparency in Bitcoin. And a lot of the transactions we process at Rebar are metaprotocol based, and debugging them is fairly difficult. So we've had to run pretty much the entire Bitcoin indexing stack to do that. And in doing that, what we noticed very quickly was all the metaprotocol indexers are completely fragmented. The databases are not shared. It's hard to work with as a developer, working with transactions or building a front end for an app. It's very difficult to interact with the data on different metaprotocols. So Bitcoin has become kind of a shared base layer for all of these different metaprotocols to store data on, but the data itself is very siloed. To walk through some examples here, and I haven't included all the metaprotocols or indexers, but this should be a good example of it. We have ordinals, which you could index with ORD or Bitcoin indexer from Hero Systems. Both of them use key value stores, usually RocksDB. In the case of Bitcoin indexer, it also uses Postgres. And the issue indexing ordinals is you need to actually track the individual Satoshi numbers. I think at some point that was optimized to track Satoshi ranges, but at the end of the day, this only really works with the KV store, even if you process the data afterwards. And what you could get from this is inscriptions or collections or anything from the basic ordinals protocol. Next up, we have BRC20, which, as far as I know, still is not supported by ORD unless you add on some extensions to it. It can also be indexed by Bitcoin Indexer, Unisat, and the OPI. Yeah, the issue here is just like ordinals, you need to track Satoshis or Satoshi ranges, and on top of that, you need to handle aggregating state across different functions. So for example, with balances, you need to track all the transfers from start to finish, which requires its own database. At Rebar, we run it with Bitcoin Indexer. It works pretty well, but point being here, we have all these different types. With BRC20s, it's a token. And then with runes, again, we have tokens with a different interface than BRC20s. We introduced cenotaphs, which would be effectively a failed rune. The hard part here is we don't need to actually track Satoshis, but we do need to handle the rune stones, which gets more complex when we go into alkanes, but there's specific logic to whether or not a rune stone is valid. And as a whole, if you're writing your own software, it becomes fairly difficult to work with. Now this could be indexed by ORD, fortunately, or the Bitcoin indexer again. And finally, we have alkanes here, which can currently only be indexed by metashrew. And I'll dive into the challenges a little bit, but first we have the protostone logic, which extends a runestone. The runestone on its own, if you use the existing software, it would fail to parse a protostone. Runestone could contain a protostone, and you could have multiple proto messages within that single protostone. So all the alkanes logic on the contract side is written in WebAssembly. One of the issues here is any existing indexers, like Bitcoin Indexer, have a pretty hard time porting over to work with WebAssembly. The way it works right now with alkanes is you run the metashrew indexing software. You compile alkanes Rust, the crate into WebAssembly, inject that into metashrew, everything indexes fine, but bringing it into another indexer is fairly difficult. And the final challenge here, probably the most significant, is handling transfers of assets. So alkanes is effectively a subprotocol of the proto-rune standard, meaning anytime an existing alkane is transferred, unless it's through a contract, it's not picked up by the alkanes indexer. You could track maybe any existing out points you have for an address, but it becomes very difficult to index this over time. And on the data side, we have a token, we have a collection, and we also have the concept of just an arbitrary WebAssembly contract, meaning the existing token standard or collection standard could be extended maybe something is mostly token but not quite, or it's an entirely new token standard, it becomes fairly difficult to work with this and index it. So one of the goals of what we worked on at Rebar was trying to design a unified API. We took a couple approaches to this, and I'll walk through them. But the biggest issue, I think, is about designing something that works across different metaprotocols. On runes or BRC20s or alkanes, each protocol defines a different standard of what a token is, for example, or what a collection is. So this is what we've tried to address. And we took a couple approaches. I think this process started around a few months ago, where we tried to use Trino to join everything together. So Trino is the SQL engine. It lets you query multiple underlying databases, even if they're different types. So this could be Postgres, could be MySQL, or MariaDB. The idea is Trino could build an execution plan that just works across all your different databases. And this actually worked fairly well for us initially. We could bring in all the existing indexer databases. It was easy to add on something like dbt on top of that. For those who don't know, Dune, for example, uses dbt to add any additional charts or tables you might need. And that was easy enough to do in SQL. Any user or developer could come in and just write some code that could, for example, extract a tokens table from all the various metaprotocols and have that as some sort of view in Postgres. Now, the next thing we did with Trino is we tried to speed up the queries by using CDC. So we would take all the existing databases, put them on AWS, and do it as S3 bucket for Delta Lake. That also worked pretty well, but that's around the time we started running into issues here. So I think the biggest one was Trino's support, just for an arbitrary bytes type, which we see a lot in Bitcoin. And for the most part, it slows queries down, particularly fixed length bytes. It didn't end up working great. Queries by block hash, for example, were particularly slow. The next issue is, and this is specific to working with ORD and also now alkanes, there's no RocksDB adapter, so you can't bring in all your existing databases. You need to write some additional logic. You wind up with kind of a mix of all the existing indexers and then a bunch of forked indexers, which is pretty messy to deal with. And the last part, and the most significant here, is when you're working with the chain tip, it becomes very difficult. Each indexer has its own chain state. Some might take 5 seconds to process a metaprotocol. Some might take 60 seconds. So you wind up having to, on the user side, add an additional logic for each metaprotocol you're working with to say, is the indexer up to date? Is everything in sync? And if one has gone down, you have to adjust your query to work with that. So we ended up scrapping this, and next up we just tried building an indexer from scratch. That was a fairly difficult task. We wrote an indexer that would work with alkanes and runes and ORD and BRC20, and it worked fairly well. It uses BRC20 as kind of an intermediate database. It uses RocksDB as the intermediate database. It works pretty well. Everything is stored. We can have a unified standard for a token. We can make sure all the metaprotocols are synchronized in terms of state, meaning we don't have to worry about on the user side is any single metaprotocol falling behind. And it makes it very easy to compose across metaprotocols. You can make a query for all tokens or all BRC20 tokens or alkanes tokens, and everything works pretty well. The issue we ran into here was, first off, the maintenance. Anytime any protocol indexer is changed because there's a bug or something went wrong in how it was initially built, you have to shut down the entire system to fix that. Everything stops being indexed. You wind up either having to resync or to sync back from a checkpoint, which is not ideal. There's a huge amount of overhead if you're bringing in a new meta protocol. You have to effectively resync the entire thing from scratch. And you wind up basically just resyncing your data over and over every time you make a change for every protocol. And if you do have an issue with a single meta protocol, if one indexer goes down, let's say you ported over the logic from a specific meta protocol and there was something wrong with it, the meta protocol can patch their own indexer and fix it quickly. But what this means for us is the entire system has stopped indexing. All the data's gone stale. It's a long process to bring everything back online. You end up with a lot of downtime. So the final approach we settled on was just using GraphQL, which means we can work with existing indexers. We can write our own. There are a couple advantages to this, but here are the three primary ones. So first off, it's declarative. So If you're actually interacting with it, you can just describe what data you want. You don't have to worry about what endpoints you're going to query if you want a BRC20 or a Rune. You don't need to worry about writing SQL joins like you would with Trino, where you're querying across multiple tables or databases. It becomes very easy to aggregate data when you have a single query. Let's say you're building a front end for a protocol and you want to know the chain tip, you want to know recent runes transactions, you want to know for a specific address were there any transactions or a specific token. It's much easier to do this with GraphQL, where most of it's handled on the server side. When we bring federation into play here, you can bring multiple GraphQL servers, define how they should interact, and it could just make a query and route across all of them. So in terms of functionality, it's similar to what Trino had, but in this case, it's much more efficient for metaprotocols, where you might have 4 or 5 or 10 different indexers running, and each has a different standard on what a token is, or if you have multiple indexers for a single metaprotocol, the types might be different. It becomes much easier to define how these should be mapped into a common type here. And finally, the results of a query are shaped exactly to match what you asked. So if you're building, again, for example, a front end to TypeScript, it becomes very easy to just define what you want, compile the types based off of the GraphQL schema, and get the result. Next up is composability here. So queries can be built from what we call a fragment, which in GraphQL is just a small part of a query. And it can be reused across different areas. So what this means is you could define, for example, I want to get a token. I want the name, the ticker, the symbol, image, and so on. And I want it for all the different protocols. You wind up with a very small amount of code to actually make that query in different places. Next up, it lets different tools like an explorer or an indexer or a wallet or anything else reuse the same logic. So it's very simple to put together an SDK that could just interact with everything. And if we wind up swapping out the backend indexers and we use something else, you write your own indexer, you don't have to worry about actually changing the GraphQL server. You can just add in something else that points to these data sources to find how the types map, and it's fairly straightforward. Next here, it encourages like schema convergence, meaning if we do have different indexers for a single meta protocol, we just have to define how they map into one single standard. And it means we don't have to worry about the different data types and the different APIs and how everything interacts with one another. And as you develop this, you find very quickly that there are a lot of shared fields in the different types. There are actually a lot of things in common with a BRC20 or a Rune or an Alkane's token. And it becomes easy to build what we call interfaces over this. So you could just define a token standard. You could define a query for top tokens regardless of the meta protocol. It becomes very easy to compose different pieces together using this. And the last part here is everything is schema driven with GraphQL. The design of whatever API you're writing that interacts with an indexer. Developers can validate all of the queries at build time, meaning you know exactly what data you're requesting, what gets returned. You know if something's invalid. It's a much smoother process for protocol developers, front-end developers, and people writing indexers generally to work with different meta protocols. So consumers always will know what's available, what you need to provide to a query, what to expect when it returns. At compile time, you can identify this. It's a fairly straightforward process. And last here, adding new protocols would usually be a breaking change if you're using a single API endpoint. You might be modifying, for example, if you had an interface for what a token looks like, you might find you have some fields that don't exist in this new meta protocol. With GraphQL, we could just deprecate it. We could mark the field as unused. We could say it's optional. You're not required to actually return all the different types. So when it comes to upgrading this and supporting new meta protocols, I think we've seen a fair number of meta protocols recently. It's a fairly straightforward process. There are no breaking changes. It works everywhere it's been integrated. So just to walk through a few queries here and then some demos. So first, just querying generic Bitcoin data. There are a lot more fields than this available, but I tried to make sure everything would fit on one page. We'll just look at recent blocks in descending order, grab 5 of them, and we'll grab these fields here. So it's pretty straightforward. We know all the types. You could query it with pretty much any GraphQL query engine. We wind up with the most recent blocks. relevant fields for them. The other benefit of using GraphQL here, specific to front-end development, is just caching mechanisms. I think the first time around this query took about 60 milliseconds. The second time we got it down to 3. It's a much more efficient process to actually build all these queries across different indexers where you might have to define E-tag caching or some kind of other caching mechanism between the indexer itself and the API. So next up here, we have runes. We're just going to grab a rune by ID, grab some common fields for it. So in this case, again, straightforward, nothing goes wrong. If it does go wrong, it just returns a straightforward error message. One of the other benefits here with GraphQL is I could query runes and BRC20s and alkanes and block information all in one query, and it's just partially returned if something goes wrong. So actually adding in new APIs makes it pretty easy to identify if there's an issue with one. It doesn't break the entire system, and everything works as expected. So next up here we have BRC20 tokens, where again we're just going to query it by a ticker. One of the unique things we could do in GraphQL here is, in this case we're using the Bitcoin indexer, which is tracking BRC20 tokens to actually grab all the different fields about a token. But here we have this address type, which maybe if we're running an Electros server, we could say we want to know, I don't know, unspent transaction outputs, or we want to know just the current value at a single address. It's easy enough to go in here and just add different fields, and the router could just say, now we need to query 2 APIs. We have to query BRC20 tokens first. We'll follow that by querying the Electrum server or something else. And it becomes very easy to compose these very large queries to interact with all these different metaprotocols that all use different databases and have different APIs all in one call. And that query would look something like this, where you have all the basic fields, you have nested fields which could contain a leaf type like address, or it could contain another struct of some sort. And the last example here is alkanes. In this case, we just feed in the ID. We request information on the API of the contract. So in this case, it's just the contract name, but it's easy enough to add in all the methods, all the fields. You could just directly query a field. GraphQL is not read-only. You can also write to it. And here we say, if it is a token, we want all these fields. So in this case, we know it is a token. And we get this data here, which is the contract, which it's Diesel, it's the Genesis token. We get the image for it, in this case through ID Club. And then we get various information on how far along it is in the minting process, how many holders there are, if there's a floor price, a market cap, and just some relevant information. And again, there are a lot more fields than this. We're just trying to keep it simple and fit everything into a slide here. But I think it's fairly easy to see just how much you could do with it when you can compose all these different APIs together. It makes it much simpler to build for metaprotocols, to interact with metaprotocols. So I think it's a much smoother process than we had with Trino. We're writing our own indexer at the end of the day. So just 2 more demos here on some things we could do with it. In this case, we'll just grab a heat map of inscription fees, which is just a basic Python script to graph it. Honestly, nothing particularly interesting here, but the next one is a little more interesting, where we could just see if we're looking at the index of an inscription for each block, we could see how much they paid in fees. You wind up with, for example, up here, some earlier transactions that were likely batching or so on, with a lot of inscriptions versus lower fees further on as you get higher up in the block. Yeah, so that's about it. I know I went through this fairly quickly, but any questions based on that? Yeah, go ahead.
You know me, I gotta start off each one with a question. So there was something that was a little bit non-intuitive for me.
Yeah.
And maybe it's because I don't know the space very well. You seem to allude, or you're making it sound like it's really important to have these indexes tightly coupled, and you would, for instance, design a lot of the things when you went over the processes of like, hey, if any of these indexers started failing, or we couldn't, index for BRC20 or runes or whatever you're doing, we would stop, or it would affect the progress of your entire like API interface or whatever of indexing the entire chain.
Yeah.
Is that because people who use like, you know, that are interested in this data are interested in the data across all the meta protocols, or is it for another sort of technical reason?
Yeah, so this came from, it's somewhere here. The approach we took of just trying to build a single indexer that could hold all the data for different meta protocols. And the advantage of using this over something like Trino would be, on the user side, you don't need to worry about, are all of the meta protocols up to date? Do we have the most recent data everywhere? If you build a single indexer to do all this, you wind up with this one process where the users aren't making assumptions that data might be out of sync or they need to check for something, and they wind up not building queries like that. So you lose most of the advantages you had if you're building one big database that indexes everything all in one go. It takes in a block, it parses it with each meta protocol standard, and it outputs some result into a database. What happens here is if something does go out of sync and it drops, you wind up having to modify all the original queries to check if each individual meta protocol is in sync. So you wind up back where you started with Trino. So in this approach, I think in hindsight, it was probably not the best way to do it, because when you do have an error, and you inevitably will, one meta protocol goes down, which means you now need to account for that across the entire system. So the final approach we took was not to tightly couple every indexer, but to run them all separately. But this is one of the approaches we took along the way.
And the approach of going separately, you sort of, again, alluded to like GraphQL being your magic bullet there.
Yes, it has its downsides, definitely. But it wound up being where we could have a new meta protocol tomorrow with its own indexer, the easiest solution to unify everything.
But GraphQL is just how the client's going to interface and query your data. What does that have to do with how you index on the back end? Or what does that have to do with whether you want to make everything tightly coupled or not? Is it
It's
just
about
because
how
of
it accesses the data. It doesn't really matter at the end of the day when you have an interface for you to say how it should interact with each database or front end. Or, well, it doesn't matter how it actually composes the data when it gives it to the client. Because of that, we don't need to worry about the indexers. We could have one go out of sync. We could bring in a new one, replace one. Everything works fairly smoothly because of that. So GraphQL in this case is not about how you write the indexer. It's about how you serve the data and how you interact with the meta protocols.
Are you finding that a lot of your users or some percentage of your users are only interested in one specific thing, or do they usually inquire about all the different meta protocols? Like, I'm just curious on some statistics there.
For the most part, you'd see it where someone might be interested in block information or address information together with a single meta protocol. That's not always the case. You might just want to grab an address and all of the various tokens, but for the most part, it's about joining Bitcoin data and specific meta protocol data. Now, this could be extended if you're doing analytics. You could say, I want to see who created a BRC20 token, and I want to see what else they hold. I want to see what else they're doing. But for the most part, it's bringing in data from Bitcoin Core or Electrum or Mempool Space API, joining it all together into just a single response to make it simple for users to interact with.
I have an idea if somebody's looking for a hackathon project to use this. A pretty common problem is if you don't do a lot of address reuse in ordinals, like if you use X first and you actually generate new addresses all the time, then you might have either BRC20 or runes airdrops on like old addresses where you were holding an inscription at some point. So if somebody wanted to make a tool where you put in an XPub, it generates however many addresses and then queries something like this and says, these are the runes, BRC20s, and inscriptions that you have at these addresses, so you can like go and consolidate all of your airdrops. That would be a super useful tool.
Yeah, appreciate that.
I'm still trying to understand. So GraphQL is just a language. So when the client makes a query, like I want for this address all the tokens across all different metaprotocols, you have some backend that then fires off requests to the different indexers.
And I probably should have put a full slide on this, but we just use federation within GraphQL, which I think was, I believe it was created by Apollo, but it basically says we can have a bunch of GraphQL servers with their own interface. We stitch them together by defining what server owns what data, how you could fetch data from another server, which is a pretty straightforward process. It's only a few lines of code. There are a few different GraphQL routers. I think Apollo is the biggest one, where you could run it, you could point it to the subgraphs. It knows how they interact, and it will route queries in an optimal way.
Sure, but like, for example, if you're trying to get information from like ORD, do you talk to the READB directly? Do you go through the JSON API? Like, how are you actually getting the data out of ORD? Like,
If we're working with ORD, we have to work with the API.
Okay, so you wrote like some sort of translation between the API and your GraphQL types.
Yeah, you just have an API client that says, here's what calls you can make, here's what it returns, and here's how the types might relate to other graphs.
Okay, and then you have some smart caching in between. So the first query, it kind of builds it in, and then it gets
Yeah,
faster
and then it's
faster.
cached for any amount of time you set. The benefit there is maybe with ORD you get a transaction ID back. You could say this is actually a transaction type. I'm just going to provide the transaction ID, and any other queries within that should be routed accordingly.
Okay, cool.
Any other questions? All right, thank you.
All right, thank you guys.